A glass bottle is fragile enough to shatter in your hand, yet tough enough to outlast mountains, surviving 1,000,000 years in a landfill. But here's the paradox. In the right factory, that same bottle is reborn in just 24 hours, melted by fire, shaped by precision air, poured back into life as something pure. Now imagine not one, but millions of bottles. Rivers of green glass rushing down massive recycling lines. Each piece sorted, crushed, and transformed into raw material, ready for a second life. Today, we're stepping inside one of the largest and most advanced recycling plants on Earth to witness the full transformation of glass, the material that never truly dies. Every day, over 25 million glass bottles are sold in the United States alone. But fewer than 1 in 3 will make it to a recycling plant. Most get tossed in household trash, shattered in dumpsters, buried in landfills. Not because glass can't be recycled, but because collecting it, clean and sorted, is harder than it looks. Unlike aluminum or plastic, glass is heavy, fragile, and color sensitive. Brown can't mix with green. Green can't mix with clear. Even the tiniest shard of ceramic can ruin an entire melt. So the journey begins not at the factory, but at the sidewalk, in the hands of regular people. Across Europe, countries have designed systems to solve the sorting problem before it even starts. Reverse vending machines, like those in Germany or the Nordics, scan each bottle, sort it by shape and color, and pay a cash refund, 10 to 25 cents per bottle. That's not just recycling, that's turning trash into currency. In cities like Berlin or Oslo, a freshly finished beer bottle doesn't go in the bin, it goes in a machine. And suddenly, it's no longer waste. It's raw material with real value. But what about the US? A few states like California and Oregon use similar refund programs called bottle bills. But most cities still rely on curbside bins where glass gets mixed with everything else. When that happens, recovery becomes more expensive. More broken pieces, more contamination, more reasons for recyclers to say, it's not worth it. But when glass is collected properly, the difference is massive. At one of the nation's largest glass recovery hubs, we followed a fleet of custom-built trucks loaded with clean, sorted bottles from supermarkets and collection points. Each truck carries up to 30,000 bottles, weighing over 12 tons. On arrival, forklifts unload towering bins and release a glittering avalanche of color. Greens, ambers, clears, crashing, tumbling, catching the light like a strange industrial waterfall. It may look like chaos, but this is order. The beginning of the recycling chain. The mountain of glass looks beautiful, but make no mistake, it's still a mess. Mixed colors, plastic wrappers, stray bottle caps, even cigarette butts. And no furnace in the world will tolerate that. So the cleanup begins, fast, loud, and precise. Giant front-end loaders dive into the piles, their steel buckets scooping up thousands of pounds per lift. They dump the shards into a massive steel hopper, where gravity and noise take over. The conveyor kicks in with a rumble, and suddenly, the glass is on the move. The first stop, a vibrating screen, a machine that shakes with brutal force, separating out fine dust, dirt, and particles smaller than 1 millimeter. This gets rid of the worst of the grime. Next come the human hands. Along the belt, trained workers pull out whatever the machines can't catch. Crumpled labels, plastic bags, juice box straws, anything that doesn't belong. But some contaminants are more dangerous and sneakier. Bottle caps, especially metal ones, can damage grinders, ruin cullet, or end up as defects in finished glass. That's why the line includes a magnetic separator. A high-powered electromagnet pulls steel and iron bits right out of the stream without ever touching the glass. For non-magnetic items like aluminum or foil, an eddy current separator takes over, using magnetic fields to repel non-ferrous metals sideways into bins. Still, some enemies are invisible to the naked eye. That's where air knives and label blowers step in. A high-speed air jet blasts the glass, blowing away anything still light enough to fly, bits of glue, foil seals, even shreds of paper. But the final, most high-tech step comes last. Optical sorting. As the glass rains down a chute like a shimmering waterfall, laser scanners analyze every single fragment, checking for shape, transparency, and especially color. The moment a brown shard appears in a stream of clear cullet, a micro puff of air fires it sideways, out of line. It happens tens of thousands of times per minute. Why so precise? Because color contamination isn't cosmetic, it's chemical. Even a 1% mix of the wrong glass can ruin the melt, leading to off-colored, brittle bottles that can't be used. By the end of this gauntlet, the material is no longer garbage. It's cullet. Tiny, jagged, clean glass fragments, each under 12 millimeters in size, sparkling like manufactured sand. And here's the twist. Cullet isn't just easier to melt. It's the secret weapon of glass recycling. Every 10% increase in cullet cuts energy use by about 3% and slashes CO2 emissions in the furnace. At 60-70% cullet content, factories can save nearly 40% of their melting energy compared to using raw sand, soda ash, and limestone alone. But before any of that can happen, the cullet has to meet strict purity standards. IMA 98% clean, moisture under 2%, no ceramics, no stones, no heat-resistant glass, because the furnace doesn't forgive mistakes. And the next stop is fire. The cullet is clean. It's sharp, it's sorted, and it's ready. But cullet alone doesn't make glass. It needs partners, a carefully measured blend of raw materials. This is where batch formulation begins, a recipe that reads more like chemistry than recycling. Each batch starts with silica sand, the core ingredient that gives glass its strength and clarity. Then comes soda ash, sodium carbonate, which lowers the melting point and makes the process more energy efficient. Next is limestone to stabilize the final structure. Depending on the product, additives like dolomite, alumina, or even metal oxides may be included to tweak color, durability, or chemical resistance. But the real hero here is still the cullet. At modern facilities, it can make up 60 to 70% of the entire batch, not just because it saves cost, but because it melts faster, cleaner, and with far less energy. Each material is weighed to the gram, then blended in a massive rotating drum until fully uniform. No clumps, no cold spots, no inconsistencies. Sensors monitor the moisture and grain size to ensure perfect mixing. Now comes the fire. The batch is fed into a regenerative gas furnace, a colossal chamber lined with high alumina refractory brick, designed to hold temperatures over 1,250 degrees, 2,300 degrees Fahr. That's hotter than molten lava. What makes this furnace special is its efficiency. Instead of letting hot exhaust gases escape, the system channels them through a heat recovery grid, pre-warming the incoming air before combustion. This regenerative cycle cuts fuel consumption by up to 30% and drastically reduces NOx and CO2 emissions. As the materials descend into the furnace, a transformation begins, one that hasn't changed in over 3,000 years, but is now controlled by computers to the second. First, the mix softens. Then it fuses. Sand becomes liquid, colorless, viscous, glowing. Technicians monitor the viscosity, temperature uniformity, and gas bubble content through laser probes and thermal cameras. Any variation can create weakness in the final glass. After nearly 24 hours in the furnace, the melt reaches its ideal state. A dense, glowing river of liquid glass moving at a controlled pace toward the forming lines. This is the point of no return. No more corrections, no more filtering. What flows out now becomes the bottle. But not just yet. Before it can be shaped, this molten glass must be portioned into perfect units, measured, cut, and dropped into molds like droplets of lava. And that is where the real transformation begins. Out of the furnace, the molten glass flows like honey. a blazing fluid ribbon glowing at over 1,000 diters, 1,832 diter. But it can't just flow endlessly. It must be cut precisely into uniform drops called gobs. A cutting shear slices the stream into measured doses, each one calibrated by weight, temperature, and viscosity. Too big, and the bottle won't form correctly. Too cool, and it won't fill the mold. Too hot, and it will collapse under its own weight. Each glowing gob is caught midair and fed into the first mold, the blank mold. This is where the double blow process begins, a method that's become the global gold standard for making hollow glass products, bottles, jars, flasks. The first blow. A jet of compressed air blasts down from above, pushing the molten gob outward against the walls of the blank mold. This creates a hollow, bottle-like shape called the parison. A glowing shell, still soft. Its neck already forming the signature bottle top. Then comes the transfer. Mechanical arms rotate the parison 180 degrees into the final mold, located just inches away. But here, every micrometer matters. The second blow, another pulse of compressed air, precisely timed, finely tuned, expands the parison fully, pressing it against the final mold's walls. In less than a second, the final shape is locked in. Shoulders, curves, grooves, and the base, formed in a single, fluid breath of pressure. Inside the forming line, every movement is synchronized to perfection. Valves open and close within milliseconds. Temperatures are regulated to the decimal. Sensors track each gob from drop to mold, ensuring that no bottle falls out of spec. Across a single line, this happens 450 times per minute. Hundreds of bottles per minute, thousands per hour, millions per week, and yet, no two bottles ever touch. Each one rides its own pocket of precision. Freshly shaped, the bottles emerge glowing red hot, their surfaces radiating in the dark like steel rods pulled from a blacksmith's forge. But they're fragile, dangerously so. Any sudden draft, a vibration, even the wrong angle, and the bottle could implode. So the system moves slowly now. Conveyor arms, cooled and padded, lift the bottles gently from the mold and place them on a moving belt. This is the path to the lair, a long, tunnel-like furnace where bottles are cooled gradually, sometimes over 20-30 minutes. Because glass doesn't just need to be formed, it needs to settle, to relieve stress, to become strong. And on the other end of that tunnel, wait the eyes, the machines, the judgment. As the bottles exit the lair, they've cooled, but not rested. Their temperature has dropped to a safe range, but inside, tiny tensions still linger. This is where the scrutiny begins. The bottles are now carried into the inspection zone, a corridor of sensors, cameras, and robotics designed to detect imperfection at scale. First, the body scan. High-speed optical cameras, some running at over 10,000 frames per second, inspect the full surface of each bottle, checking for cracks, blisters, bubbles, or warping. Even a hairline fracture under 0.1 millimeter will cause a bottle to be rejected instantly. Next, the neck inspection. An automated carousel rotates each bottle, while laser sensors and precision probes measure the finish, the lip, the threads, the sealing surface. If there's a chip, a tilt, or a microscopic flaw in symmetry, the system flags it in milliseconds. This isn't just quality control, it's trust insurance. Because a faulty bottle doesn't just break. It risks leaking, exploding under carbonation, or contaminating what it holds. Only the bottles that pass every test move on to the next stage, palletizing. Here, robotic arms take over again, not to shape, but to organize. A vacuum clamp picks up entire rows of bottles, setting them onto pallets layer by layer. Between each layer, a protective sheet is placed to absorb shock during transport. Once the stack is complete, usually hundreds of bottles per pallet, a plastic wrap spins around it with tight precision, securing the load into a single block. A QR-coded label is printed and slapped on the side, carrying full traceability. The batch, the furnace, the forming line, the timestamp. From here, the pallets enter cold storage or are loaded directly onto trucks, destined for bottling plants, beverage companies, or export terminals. And that's where we find our next stop, the Coca-Cola bottling line. At one facility in the Midwest, pallets of freshly made bottles arrive at dawn. They're unloaded, unwrapped, and moved straight into sterilization, a chamber of hot water jets and high-pressure steam designed to wipe out any microbial risk. From there, the glass glides onto the filler line, a high-speed belt that can handle over 60,000 bottles per hour. Nozzles descend from above, filling each bottle with Coca-Cola down to the exact milliliter. Simultaneously, a burst of CO2 gas is injected, locking in the fizz that defines the drink. Next, the capping station. Crown caps are pressed down by precision pistons, each one tested for seal integrity on the spot. If the cap is too loose, even by a fraction of a millimeter, the system rejects it. Then, the labeling line, where branding meets precision. Labels are applied, scanned, checked for alignment and registration. Finally, the bottles are sprayed with cool water to drop their temperature and roll off into their shipping cartons. From here, they move across the world, into gas stations, diners, stadiums, and grocery shelves. From a pile of broken shards to a sealed bottle of the world's most iconic soda. It's a transformation, not just of form, but of meaning. And the best part? When that Coca-Cola is gone, the bottle isn't. Because if it finds the right bin, the journey begins again. Hold a glass bottle in your hand, and you're not just holding a container. You're holding the ghost of 100 lifetimes. That clear gleaming surface was once a broken shard. Before that, it was sand pulled from ancient earth. Before that, it might have been another bottle, in another decade, on another shelf. Glass doesn't age, it doesn't degrade, it doesn't vanish, and it doesn't need to. Because unlike most materials, glass was built for the long game. Through heat, through force, through precision, we've seen how it transforms, again and again, without losing a single molecule of potential. But what makes this story remarkable isn't just the chemistry, it's the system that makes it possible. From curbside bins to reverse vending machines, from cullet specs to regenerative furnaces, from double blow forming to laser inspection. It takes 1,000 coordinated decisions to turn waste into worth. And when that system works, we don't just recycle glass. We recycle energy, resources, and trust. We reduce emissions. We reduce mining. We reduce the invisible cost of convenience. So the next time you finish a soda and feel the weight of the empty bottle in your hand, don't toss it without thinking. Because what looks like just a bottle is actually a passport. One that's already traveled through flame and steel and is ready to go again. What did you see today? Just bottles being made? Or a hidden world of engineering, chemistry, and second chances? If this journey changed how you see glass, imagine what we'll discover next. From concrete to solar panels, from cardboard to copper wire, the industrial world is full of stories where everyday materials live extraordinary lives. So tell us, what should we explore next? Drop a comment with a material you want us to break into. We read every one, and if this story sparked something in you, if it made you think, or feel, or see your soda bottle differently, give it a like. Share it with someone who still thinks glass is just glass, and subscribe for more journeys into the machinery that makes our world. Because sometimes, a bottle is just a bottle, and sometimes, it's a mirror reflecting everything we can do when we design with care and close the loop.